Hi, I am Keshav of CSC Data Science. Today our topic was the multivariate normal distribution. Our main objectives are normal distributions, white-rank transformations, linear discriminants. Resources for this PowerPoint is DHS Chapter 2 Part 3, KF Intro to PR, Exit PR course, MH Gaussian discriminants, EM linear discriminants. Multi-category decision services. Define a set of discriminant functions g of x is I equal to 1 to c. Define a decision rule. Choose omega I if gi of x is greater than ji of x for every j is not equal to 1. For Bayes classifier, let gi of x is equal to minus r into alpha I by x because the maximum discriminant function will be correspond to the minimum condition of risk. For the minimum error rate case, let gi of x is equal to p omega I of x so that the maximum discriminant function corresponds to the maximum posterior probability. Choice of the discriminant function is not unique. Multiply or add by the same positive constant. Replace g of x with the monotonically increasing function f of g of I of x. Network representation classifier. A classifier can be visualized as connected graph with arcs and weights. Action, classification, g of I of x, g2 of x, and so on up to ge of x. Input is x1, x2, x3, and so on up to xt. For discriminant function, costs are applied. What are the advantages of this type of visualization? We may know now. Log probabilities. G of I of x is equal to p omega I by x is equal to p x by omega I p omega I by sigma j equal to 1 to c p of x by omega j into p of omega by j. Gi of x is equal to p x omega I into p omega I. F of gi of x is equal to ln of gi of x is equal to ln of p of x by omega I plus int p of omega I. What are some reasons is particularly useful? Computational complexity, example Gaussian. Numerical accuracy, example probabilities 10 to 0. Decomposition, likelihood and prior are separated can be weighted differently. Normalization, like likelihoods are channel dependent. Decision surfaces. We can visualize our decision rule several ways. Choose omega I if gi of x is greater than gj of x for every j is not equal to I. Here we can see the diagrams of gi and gjx. R1, R2, R3, R4, R5, R6 are the decision surfaces, and we can in the right image we can visualize in a 3D form. A classifier that places a pattern in one or two classes is often referred as diachromatizer. Here we now going to discuss about two category case. We can rephrase a decision rule if g1 of x is greater than g2 of x. That implies g of x is equal to g1 of x minus g2 of x greater than 0. If you use log of the posterior probabilities, g of x is equal to p omega I of x minus p omega 2 of x. F of x is equal to ln of g of x is equal to ln of p of x omega 1 by P of x by omega 2 plus ln of p omega 1 by p omega 2. A diachromatizer can be viewed as a machine that computes a single discriminant function that classifies x according to the sign. Examples support vector machines. A classifier that places a pattern in one or two classes is often referred to as diachromatizer. We can reshape the decision rule if we use a log to the posterior probabilities. A diachromatizer can be viewed as a machine that computes a single discriminant function and classifies x according to the sign. Examples support vector machines. Recall definition of a normal distribution, Gaussian. Now we are going to discuss about normal distributions. P of x is equal to 1 by 2 pi d by 2 by sigma 1 by 2 exponential of minus 1 by 2 x minus mu whole to the power of t sigma minus 1 into x minus mu. Mean. Mean mu is equal to e of x is equal to integration of xp of x dx. Covariance. Sigma is equal to e into x minus mu into x minus mu whole to the power of t is equal to x minus mu into x minus mu whole to the power of t p of x dx. Statistical independence, higher order moments, Occam's razor, entropy, linear combinations of the normal random variables, central limit theorem. These are the questions are raised for the normal distributions. Univariate normal distribution. A normal or Gaussian density is a powerful model for modeling continuous value feature vectors corrupted by the noise due to analytical traceability. Univariate normal distribution. Univariate normal distribution. P of x is equal to 1 by root 2 pi omega sigma exponential of minus 1 by 2 into x minus mu by sigma whole square, where mean and covariance are defined by mu is equal to e of x into integration of minus mu to mu, minus infinity to infinity, like that. The entropy of a univariate normal distribution is given by h of p of x is equal to minus omega minus infinity to infinity and follows. Mean and variance. A normal distribution is completely specified by its mean and variance. The peak is at p of mu is equal to 1 by root 2 pi sigma. 66% of the area is within 1 sigma, 95% is within 2 sigma, 19% is within 3 sigma. Normal distribution achieves the maximum entropy of all distributions having the given mean and variance. Central limit theorem. The sum of large number of small independent random variables will lead to the Gaussian distribution. The multivariate normal distributions. A multivariate normal distribution is defined as where mu represents the mean vector and sigma represents the covariance matrix. Note the exponent term is really a dot product or weighted Euclidean distance. The covariance is always symmetric and positive semi-definite. How does the shape vary as a function of the covariance? Support regions. A support region is obtained by the intersection of Gaussian distribution with a plane. For the horizontal plane, it generates an ellipse through whose points are equal to the probability density. The shape of the support region is defined by the covariance matrix. Derivation. Let 1 by root 2 pi 1 by 2 pi root mod c is equal to k. Applying both log on sides, of Gaussian equation. The equation of the support region is original space is x square by a square plus y square by b square equal to 1. New axes of rotation are defined by x is equal to x dash cos theta minus y dash sin theta, y is equal to x dash sin theta plus y dash cos theta. Angle of rotation for support region is given by tan theta is equal to 1, sigma x square minus sigma y square plus or minus square root of sigma x square minus sigma y square whole square plus minus 2 sigma xy whole square by minus 2 sigma xy. Identity covariance. Gaussian distribution with identity covariance matrix has equal variances in all directions. Support region for the Gaussian distribution with identity covariance matrix C100 is a circle. Unequal variances. Support region for the Gaussian distribution with the covariance matrix C5002 is an ellipse aligned with respect to the original axis. Non-zero of diagonal elements. Support region for the Gaussian distribution with covariance matrix C is equal to 1, 0.5, 0.5, 1 is an ellipse rotated at an angle of 45 degree with respect to the original axis. Unconstrained of or full covariance. Support region for the Gaussian distribution with covariance matrix C is equal to 5, 0.5, 0.52 is an ellipse rotated at an angle of 9 degrees minus 81 degrees with respect to the original axis. Coordinate transformations. Why it is convenient to convert the arbitrary distribution to spherical ones? Hint: Euclidean distance. Consider the transformation A omega AW is equal to phi of A power minus 1 by 2, where phi is matrix, the whose columns are orthogonal eigenvectors of omega, and the derivation is as follows. Mahalanobis distance. The weighted Euclidean distance x minus mu whole to the power of t into sigma minus 1 x minus mu is known as Mahalanobis distance and represents the statistically normalized distance calculation that results from widening transformation. Consider an example using our Java applet. Discriminant functions. Recall a discriminant function for a minimum error rate classification. For multivariate normal distribution, consider the case statistical independence or equal variance, class independent variance. Gaussian classifier. Discriminant function can be reduced to, since these terms are constant with respect to the maximization, we can expand this as the term x dash x is constant with respect to I and mu I is a constant that can be pre-computed. Summary. Decision surfaces geometric interpretation of the Bayesian classifier. Gaussian distribution. How is the shape of the distribution influenced by mean and covariance? Bayesian classifiers for the Gaussian distributions. How does the decision surface change as a function of the mean and covariance? Thank you.